Imagine standing in front of a wall with two narrow slits cut into it. Now imagine tossing tennis balls at that wall, one after another. Some balls will hit the wall and bounce back, but some will fly straight through the slits and hit a second wall behind. If you mark where each ball hits the back wall, you'd end up with two neat clumps of marks, each clump right behind one of the slits. This makes perfect sense to us. Tennis balls are particles, they travel in straight lines, and they go through the slits like tiny bullets. Now, let's swap out the tennis balls for a wave. Picture tossing a pebble into a still pond. It creates ripples that spread out. Shine a light of a single color one wavelength at the same two-slit wall. Light is a wave, remember, so as it encounters the two slits, each slit becomes a new source of waves. These waves spread out and overlap behind the wall. Where a peak of one wave meets a peak of the other, they reinforce and make a bright stripe. Where a peak meets a trough, they cancel and make a dark stripe. On the back wall, instead of two clumps, you'd see a series of bright and dark stripes, a beautiful interference pattern of light. This is exactly what Thomas Young saw back in 1801 when he first did the double-slit experiment with light, proving that light behaves like a wave. So far, so good. Two slits, tennis balls particles gave two clumps, waves gave many stripes. Now, hold on to your intuition, because here comes the twist that demolishes common sense. Replace our tennis balls and light waves with electrons or single photons. It works the same way. Electrons are the tiny particles that make up atoms, so you might think they should act like the balls. Solid particles traveling one at a time. First, block one of the slits so electrons can only go through the other. As electrons hit the back wall one by one, they leave dots that form a single clump behind the open slit, just like the tennis balls. So far so classical. Next, open the second slit again. Now, do exactly the same thing. Fire electrons towards the wall, but let them pass through the two slits. Intuition and common sense tells us there are two slits, so each electron should go through either the left or the right slit and hit the wall in roughly two clumps like the tennis balls earlier. However, the very opposite happens. Instead of two clumps, the dots on the wall gradually fill in to form an interference pattern, the same stripe pattern we saw with waves of light. Every time an electron hits, it's just a single dot. But as you fire more and more, even firing them one at a time, waiting a few seconds in between each shot, the dots accumulate into bright and dark stripes. It's as if each electron, all by itself, is somehow passing through both slits at once, behaving like a wave that goes through both openings, then interfering with itself. This is the first mind blow. Each single electron is interfering with itself. We didn't fire them at the same time, so they couldn't even meet each other in flight. Yet the final pattern is identical to what overlapping waves would make. A single electron seems to take two paths simultaneously, a completely foreign idea in our everyday world. To drive the point home, if you only had classical intuition, you'd expect particles equals greater than two clumps, waves equals greater than stripes. But the double slit shows electrons particles giving stripes. Common sense just got flipped on its head. Now, let's add one more twist. Up until now, we've been not watching which slit the electron goes through. We just collected data on the back wall and let the pattern emerge. But suppose we try to peek and place detectors at the slits, tiny sensors that click whenever an electron passes. We only need to know, did the electron go through the left slit or the right slit? One might think, it shouldn't matter. The electron already formed an interference pattern, so knowing the path after the fact is harmless. Sadly, no, it matters a lot. As soon as we measure and learn which slit the electron goes through, the interference pattern disappears entirely. Instead of stripes, you now get to clumps, just like with tennis balls. By watching, we force the electrons to behave like ordinary particles going through one slit or the other. It's as if the electrons know they're being observed. This is the second mind blow. The act of observation changes the outcome. In quantum experiments, just looking or measuring is not passive. When the detectors are on, the electron decides, okay, I'll just go through one slit, no funny business, and the mystery vanishes. Turn the detectors off, and back come the wavy, striped patterns. The mere potential of getting which path information destroys the wave behavior. Even if the detector is so gentle it barely touches the electron, the interference still collapses. It's not a trick, it's fundamental. In quantum physics, knowledge and reality are intertwined. So what is happening? How can a particle choose its behavior? Physicists explain this with wave-particle duality and superposition. The electron is described by a wave function, a fuzzy cloud of probability that can pass through both slits at once. When the electron isn't measured, the wave function evolves and interferes with itself. But as soon as we measure it even gently, that wave function collapses to a definite outcome. Mathematically, quantum rules work out beautifully, but intuitively it feels like magic. It's almost like the electron will do anything except follow normal logic. To give it a spin you might relate to, think of an optical illusion that flips between two images like the famous faces drawing. At first glance, your brain holds both images in an unresolved state. Then you focus, and suddenly one image clicks into clarity. The other vanishes. In the double-slit experiment, the electron's wave carries both possibilities left slit and right slit. If you don't look, the possibilities overlap like seeing the ambiguous illusion in limbo and make a pattern. The moment you decide to look, focus your mind with a detector, the overlap breaks and only one reality is seen. It's like reality itself is an unresolved illusion until we force it to choose. This goes against our everyday intuition, our so-called common sense. In the macroscopic world, if you shine a light on something or take a photo, the scene itself isn't altered just because you're observing it. But in the quantum world, observation is part of the phenomenon. It reminds us of a common cognitive bias. We assume our worldview doesn't change merely by watching. But quantum mechanics slaps that bias aside. Even famous physicist Richard Feynman said that the double-slit experiment contains the only mystery of quantum physics because of how it defies logic. If anyone tells you they can explain it using plain common sense, they're not being honest. The experiment simply doesn't comply with common sense expectations. What does this mean philosophically? It suggests reality at the smallest scale is nothing like we imagine. Particles don't have definite histories until measured. If nobody looks, electrons go through both slits as a wave, and only when we measure do they choose a path. It's similar to Schrödinger's cat, the famous thought experiment where a cat is both alive and dead until observed. Only here, it's real experiment, not a cartoon. It forces us to ask, is there a single objective reality when we aren't looking? Or does reality depend on observers? Practically speaking, this isn't just academic. The same principles of wave-particle duality underlie modern technology. Electron microscopes, for example, use electrons like waves to see tiny details far beyond what light can resolve. Quantum computers rely on particles being in multiple states at once until measured. So this common-sense destroying experiment is also the foundation of next-generation tech. In other words, nature might laugh at our intuition, but nature doesn't lie. In summary, the double-slit experiment is like a cosmic magic trick that shows our expectations can be completely fooled. It teaches us a kind of mental humility. Things at the quantum level just aren't as straightforward as everyday objects. So the next time you catch your brain being fooled by an optical illusion or a mental shortcut, remember that even particles get tricked by quantum illusions. And sometimes, the very act of paying attention, the mind's version of observation, can change what you see. Thanks for watching this mind-bending journey into quantum physics. If you enjoyed having your common sense destroyed in a good way, give us a like and share with a friend who loves puzzles. Hit subscribe to Philosora for more weekly dives into illusions, brain hacks, and philosophical experiments. Let us know in the comments, how has this experiment warped your sense of reality? See you next time for another mind-twisting adventure.